Okay, good morning everybody and welcome to our Fossil-Free Future seminar. I am your host and the host of the seminar and moderator of our panel discussion later in this seminar. And my name is Pia Karuma and I'm also the lead of this Fossil-Free Future Veturi program. So this is the agenda of our seminar. So I will tell you a few words about the program, and after that, Professor Eija Tanskanen from the University of Oulu will tell us about the Arctic natural hazards role in the European resilience and energy solutions. And after that, Tuomas Hakala from Convion will tell us about the advancements and prospects in the development of Convion's solid oxide electrolyzers for green hydrogen production. And after that comes the panel discussion, and we have the panelists here sitting in the front. And please notice that the audience has also a role in the panel discussion, so you have a chance to comment or ask questions, of course, in the time constraints that we have. And we will end the seminar at 12 o'clock. So that is how we are going about. Right, so a few words about the Fossil-Free program. So it's a five-year-long program that started last year, will end 2027. And it's partly funded by Business Finland, and that's why it's also called Veturi program. We are building a power electronic ecosystem of fossil-free electronic solutions for industry, transportation, and energy conversion. And in the program, we have three themes. The first one is called Highly Efficient Smart Power Electronics, Sustainability and Digitalization. And the second one is called Off-Highway Vehicle Electrification, Smart Energy Storage Solutions and Charging Infrastructure. And the third one is Efficient and Cost-Competitive Green Hydrogen Production. And now next, Professor Eija Tanskanen will tell you more about the Arctic natural hazards role in the European resilience and energy solutions, and a few words about Eija before she comes to the stage. So she is a director of Sodankylä Geophysical Observatory of the University of Oulu. Eija is a doctor of philosophy with theoretical physics as a major, and she has been a professor of space physics for nearly 20 years. She has worked abroad in the US at NASA Goddard Space Flight Center, University of Bergen in Norway, CERN Accelerator Laboratory in Switzerland, and at the University Center in Svalbard, Norway, which is the world's northernmost university. Her main research topic is natural hazards and their effects to the critical infrastructures. Eija is also exploring how solar disturbances transport energy to the atmosphere and on ground. Eija, the floor is yours. Thank you.
So, ladies and gentlemen, let's talk about natural hazards. That's my topic of research, and all different disciplines where that information is needed. And it might be that some of that information is also needed for this research field when new fossil-free hydrogen solutions are worked out. So I will first describe the physical phenomena. So what am I talking? So what is the physics and what kind of phenomena? And why we have them? Then we go for European resilience for a while. How do we need to take it into account in Finland nationally and European-wide and globally? And last, we can talk a bit about how it affects the energy solutions and solutions what we are innovating here today. Sun is the source, ultimate source of the energy for our planet. So it would be quite a cold here, close to the absolute zero without the energy from the sun. So that is needed for us, for everybody to be here. And there is a very interesting physics inside the sun what makes sun to produce that huge amount of energy that fast and release it so fast. So maybe the nature can teach us something. So when we explore physics in detail, maybe we can find some solutions, some tips for innovations also here on ground level. And that picture there on right-hand side, yes, right-hand side, is on a scale. So that small dot there is our planet. And that loop there is the disturbance what sun is releasing. So pretty huge. And when we are talking about how does that structure there on the surface of the sun affect us, we are talking about very high energy particles. We are talking about magnetic fields that are twisted, because then the energy can be transported. It's like a Christmas present. It's a package that delivers the energy. And if the package is loose, then all the energy just go somewhere in a space. But if the package is tied very nicely, very well, then the energy is transported to the Earth and to our atmosphere. And then it has all kind of nasty effects there. And those effects affect us because we are in a close vicinity of the sun. So we are connected, magnetically connected. And I'm talking now about electromagnetic phenomena. So sometimes you might hear the word space weather, and it refers to electromagnetic phenomena. And because energy solutions are very often equipments, then there is an interference between these phenomena with these equipments. So solar wind is blowing from the sun towards us. It's very fast. It's 10 times faster than any bullet, the fastest bullet what we can have here. So it's really going fast. And whatever we put to the space, for example, satellites, they are destroyed very easily. So it's very hazard environment. Luckily, we have some protection, the magnetic field, you can see here, produced by the Earth. So we have a good shielding, pretty good. But every now and then, the disturbances, big solar storms hit us and cause huge economic loss. I have picked up few examples. When we lose, we have built a society which is dependent on satellites very much. Each of you have in your pocket possibly a device which is dependent on satellite. And if that satellite is not working, then your cell phone is not working. And whoever is using electricity is dependent on this. Whoever is using water is dependent on this. We just don't maybe see it because we have built quite good society, quite resilient society. So typically, if everything is functioning well, we don't think that somebody is taking care of this thing. When nobody is taking care of something, then you start seeing problems. So, okay, so if we lose one satellite, then it might mean that for 1 week or for 1 year or 1 day, you lose the services what are dependent on that specific satellite. And already 2013, Lloyd's computed that it might be over 100 million of value what the company have lost because of that one day of loss of satellite signature and services that are based on those. So we are talking about big money here. And very recently, 40 new Starlinks were lost because nature were not appreciated. Usually, it's easy to see whether it's good weather or bad weather outside, like today. But because we don't have a sense for magnetic field, so we don't see whether it's good or bad magnetic weather outside. So we need to appreciate the measurements. So we need to check what are the conditions. And it's not routinely yet done, as you can see. 40 satellites just up and then down next day. We have all that information available, but it's not in a right place. So we should make sure that we have all that information in a right place where the decisions are made. Okay, few examples what could happen and what has happened. When solar storm hit us and our infrastructure, it might burn transformers. This is from the electricity network. So it's 1 minute and the transformer is burned because of the overheating and huge currents. So this is what is happening for the infras. And whoever are dependent on this suffer about the loss of this. Then lightning is one fascinating phenomena which is not completely understood. But it looks like lightning is also powered by the solar energy. And I probably shouldn't talk about solar energy because I should talk about energy from the sun. Solar energy have a specific meaning in Finnish and English language. So I'm talking about all energy forms, not only radiation, but all energy forms coming from the sun. So less than in millisecond, we will get more energy from the space to the ground in a form of lightning, more than what we can produce here in Earth with any of our power plants. Less than a millisecond. That's why it's burning houses. That's why it's causing problems with people if we are hit by lightning. And that science is not understood. So if we could harness that energy, we would need to have devices that can take energy that fast. And I don't know whether I can even hope to have such devices. Everything would get burned right away. It's so huge amount of energy. But I'm very keen on trying to find a solution. But I don't know whether we are yet there. But let's at least discuss. Okay, so we have a good protection. Nature have built around Earth magnetic field that safeguards us here. Even if we recognize it or not, it's working quite okay. But it's leaking in some places. There are some places there which are not so well protected, like here, you can see. So space will come very close. So atmosphere is closer here at 8 kilometers and here at 16 kilometers. So space will come closer here in Arctic regions where we are. So that we need to take into account. And it is very well known auroras form in these regions. And that is because of that energy. So they don't form to equator, they form here. In reality, the field is not quite very smooth and symmetric. It's pretty messy, and it's leaking every now in some places more than in other places. And in Sodankylä, we have measured 110 years of this leaking. And you can see from this red curve, that is because of that messy thing. The protection has weakened 30% in 100 years. In other places globally, it has decreased 5%. So space is affecting for us more than others. The red and blue curve is because of sun, and this orange and blue are because of sun, and the red one is because of that messy thing inside the Earth. Luckily, we also have atmosphere that is little bit damping the effects. So some of the highest energy particles are just damped in some of those surface layers what we have in atmosphere. And space debris, for example, is burning most of that, and only small pieces are coming to the surface of the Earth. So in European level, there is a legislation. It actually was already 2010 or so. New legislation came that each EU country need to identify risks for their country. And Finland identified 6 risks, and solar storm was one of those. So since 2015, Finland have acknowledged that solar storm is one of the largest risks for our society. In addition of pandemic, for example. They are in the same list. Okay, then space debris is the new thing. Because we have sent out to the space so much satellites, we have started to produce debris as well there. And that debris will come to the ground every now and then. So new legislation was accepted last year about critical entities resilience. So this is the continuation for national and regional and European level risk assessments. So now we need to define which are our critical entities in Finland, what we need to take care of, so that we can secure other functions. And we have in Sodankylä at observatory few of those. Not all, these are all our frequencies. If you talk frequencies, then you can see all the measurement frequencies what we have. If you don't talk fluent frequencies, then you can see that megahertz means 300 meter wave, gigahertz 300 millimeter wave, and millihertz 300 million kilometers. This is the distance between sun and Earth. So best we can get information from sun from that frequency. So this shows you a long timeline of our measurements. And now, when Finland is leaving our first year of NATO era, the importance of these measurements, which were started 110 years ago, have become more and more important. So many of these have already selected as a NATO critical assets. Last week I was in a NATO science meeting where we discussed about which might be critical for them and which not, and most of our radars will be part of that. Then we come to the ground. So it has been known decades that all long infrastructure, whatever you build, long this way or horizontal or vertical, then you will get induced currents and large amplitude currents. So it has been taken into account whatever we have built, whether it comes to the oil drilling, so that needs to be taken into account, or whether we build some gas pipelines. That has been taken into account when those have been first time designed. So that's why this needs to be taken into account when this new thing is planned. So otherwise, in few years, that pipeline is corroded because of currents from space. So whatever was built underwater, it was taken into account in a design. Then, in addition of the currents, we have new threat. We have always had meteoroids coming to the surface of the Earth, but that happened pretty rarely. You might have found one meteoroid, or you might know somebody who have seen something related to space stones. But now when we start having more and more up there, so it means that we will get also more and more down. So typically 300, 400 of that kind of space debris will come down to the surface. 300 pieces every hour. And it's about 40,000 kilograms material hitting somewhere. And we cannot control it. So it just comes somewhere. Sometimes they are typically like a few centimeters, 10, 15 centimeters. But they might be that big. There haven't been many human losses, so this is not very dangerous, so you shouldn't lose your night sleep or anything. It's only 2 persons have been killed because of that hitting them in entire history. But we need to understand that it's a possibility. And somebody needs to take care of that, not you. You don't need to worry about that, but somebody in Finland. So we need to have an office that take care of that, and we don't. Finland is a very small space country, so to say. It's large, but it's small in space business. But we still have the same threat as others. And somehow we need to find a way to cope with this. So what are the benefits on having green hydrogen solutions? I didn't went very far from atmospheric chemistry because it's not my research area. But what I have understood, and please correct me if I'm wrong, it looks like when we have this new type of energy form, it makes atmosphere more clear, and that's because it changes the composition of the atmosphere. And it looks like it even increased the ozone layer thickness of that. So it looks like the science shows that, and it makes the air more clean. So, but there is work to do in scientific point of view, and there are a lot of scientists in Finland doing this research. We are not doing it very much at Sodankylä Geophysical Observatory, but it looks like it's a very positive signature. And that figure shows you the atmosphere. There are different layers. During nighttime, it's very simple structure, few layers, but during daytime, when the sun is giving more heat, we will get more of these layers. And those layers are the reason why the signature from the satellite is not coming very well always. And other way around, if we are doing radar, sending radar signature up, it might never come back down because of those layers. They will make nasty things for the signature. Okay, then I have questions to you. So what might be, this is one instrument what we are building at the moment to Kilpisjärvi. So they are huge. So what might be good energy solutions? So running that instrument requires huge amount of energy. What we can get it to there? What would be the good solution for having the energy for running that instrumentation? Do you have a solution for that? Or do we need innovations? Or do we just do it as we used to do? Then we have this type of instrumentation, huge antennas. And these antennas are in Sodankylä because they need a very sensitive place. So we cannot have disturbances coming from our life there. So what kind of energy solutions might be good for that kind of instruments, where we cannot have very much moving parts, no very much big currents anyway. So I don't know what would be a good solution for that. Then we have instruments in very remote places. So this needs to be out of any electricity lines. So is there any way of getting energy? Now we are using diesel. I don't like it. We just carry it there and use it. Is there any other solution what we can work out? It's not a good one, but it's the only one so far. So there are many open questions here. Let's try to find answers. Our resilience, our own society's resilience needs that, and European resilience needs that. So let's try to scope with these challenges and try to find solutions here today with you. Thank you.
Thank you, Eija. Do we have any time for questions? Yeah, okay. So at least one question from the audience, if anybody has a good question in his or her mind. Yeah, it was really exotic, I would say. Yeah, gives a lot of thought. If there aren't any questions yeah, there's one question, please. There's a microphone coming to you, so.
Maybe not so educated, but do you mean that you want a battery there instead of the grid?
Whatever
on your previous
solution.
slide?
Yes, whatever
Something.
solution you can give me, I'm happy to take it. So, we can try.
Yeah. It would be good if the solution was fossil-free.
Oh, yes.
Yeah. Yeah. Good.
Thank you.
Thank you, Eija. And then, do you have the... Oh, it's here. Let's change the slide. Okay, so now comes Tuomas Hakala from Convion, and he will tell about the advancements and prospects in the development of Convion's solid oxide electrolyzers for green hydrogen production. And before the stage is for Tuomas, a few words about him. So Tuomas is a co-founder of Convion, a Finnish technology company commercializing electrolyzers and fuel cell products for decarbonizing hard-to-abate industrial sectors and power generation. Convion's products are based on high-temperature solid oxide cell technology, offering unparalleled efficiency compared to other technologies. Tuomas has worked with high-temperature electronic systems for 17 years, first in Wärtsilä and later in Convion. He has had multiple roles ranging from fundamental systems R&D to supply chain development. Tuomas has been granted several fuel cell and electrolyzer system-related patents. In his current role in Convion, Tuomas is responsible for applications and business development. Please, Tuomas, the stage is yours.
Thank you, Pia, for the introduction and this opportunity to tell a little bit about Convion and Convion's developments around solid oxide electrolysis technology. How do I start? Okay, a few words about Convion as a company. Convion is a technology company, very narrowly focused on high-temperature electrochemical systems, and underlining the word systems. We don't do the electrochemistry, the cells or cell materials, but focus on the systems integration, process technologies, automation, software, and power conversion. The development started very early on in the 2000s within Wärtsilä R&D. That's where all the founders came from, and then the company was established in 2012. Always focused on industrial scale, fuel flexible, and robust systems. You see the imagery. These are historical images, sometimes from complex and demanding application areas. And we are so-called stack agnostic, so we operate with the leading providers of cell stacks for our systems. Solid oxide technology, most of the time you hear about electrolysis and hydrogen, you hear about the earlier generation technologies, alkaline, which is ages old already and very mature and scaled up, or PEM electrolysis. Solid oxide is somewhat different. I would say it's less mature at the moment, but it holds a lot of promise because of the high temperature. It's not dependent on critical minerals, and it has higher conversion efficiency compared to any other technology when considering conversion from gas to power or power to gas. So that is the ultimate selling point. In addition to that, it is very tolerant to non-commodity feedstocks and various compositions of feedstocks. And today we talk about electrolysis. You see here the two products basically very much resembling each other. On the left-hand side, you see a mini fuel cell system. It's a 60 kilowatt mini power plant with high efficiency, and it's fuel flexible. And nearly the same, 75% parts commonality, you see a 250 kilowatt electrolyzer system on the right-hand side. This is a steam electrolyzer, splitting steam to oxygen and hydrogen with electricity. And it's designed to have an efficiency of over 85%. That means steam is given, so this is the amount of, if you divide the lower heating value of the hydrogen produced by the electrical inputs altogether, then that's how you reach 85%. Because of its sort of DNA as a fuel cell system, it can also switch directions and operate bidirectionally. And we can also use carbon dioxide as a co-feedstock with the system and produce syngas for petrochemical industry, for example. Here on the lower row, you see the electrolysis key applications that we have identified. Today, of the final energy, only 1/5 is roughly electricity, and we see the big electrification trend, but there will be also need for molecules, and we believe that the most robust and future-proof application spaces where molecules are needed, and that, such as green steel, ammonia, and e-fuels, either carbon-based or not carbon-based e-fuels. I mentioned the efficiency and said that when steam is given, that highlights the possibility of industrial integration. When you have industrial processes as off-takers of hydrogen, and they might have excess heat, and that heat can be used for steam generation. And I'm not going to lecture about thermodynamics, but here you see the chart. While we go up in temperature, part of the energy input can be given in form of heat, and then you need less of electricity. And this is what creates a sustained difference compared to the legacy technologies of alkaline and PEM. And this system actually consumes heat, does not produce heat. This is a picture of the first-of-a-kind demonstration that we carried out last year in Espoo, Finland, together with VTT and a bunch of other companies. It was a very cross-cutting project where we, in the end, produced synthetic diesel and operated the tractor with that diesel. And we produced hydrogen for that and reached the design point of over 85% electrical efficiency and very promising cycling results over 1,000 cycles of test period. This shows a little bit about the comparison between PEM and alkaline. You see the bars, there's PEM and alkaline, the energy. These are already mature, so only incremental improvements are expected. This is the amount of energy that is needed per normal cubic meter of hydrogen. Then you see the proto bar and then the future possibility bar of our solid oxide. And there is a difference already in total length, but the red part of the bar shows the amount of energy that can be fed as heat, and that creates a 25 to 30% difference in electricity needed per kilogram of hydrogen. This potential of up to 95% efficiency can be reached by improving the thermal self-containment. All the heat lost is lost, and that must be mitigated, and we are working on it. And then some improvements in power electronics. The topology, particularly when scaling things up, can be done differently, and we see 95% maybe as a ceiling to be reached, north of 90 anyway. Scaling of these systems will be incremental. It depends on the maturity of the cell stacks. Here you see the artist's illustration of a system with those little boxes that are megawatt each, and we plan to have multiple of those integrated together. And these are the stepping stones. The 250 kilowatt is an industrial demo size, and with that we build showcases around the world. But expect to demonstrate the megawatt scale module in 2025 or 6. The bidirectionality is a built-in feature, and co-electrolysis is an interesting added value in petrochemical industry particularly. We see that these will eventually anyway be modular, so we will not build a massive monolithic system. This must be factory manufactured and logistically easy. But clearly the demand is in tens and hundreds of megawatts at least, and that's what we are addressing with the new design. So far we've demonstrated the first system, reached the design efficiency, produced synthetic diesel, connected all the different parts of the puzzle. And we have designed the co-electrolysis and the bidirectionality as features, but they remain yet to be shown. The co-electrolysis basically is steam electrolysis, comparable to steam electrolysis, but it reduces capex in the synthesis chain, so you have less of reactors, and that streamlines the process of, let's say, Fischer-Tropsch or methanol synthesis. Okay, I will close with that. I didn't go over time, and I'll be happy to answer questions.
Thank you, Tuomas. Right, there's one question here on the second row. Please, could you wait for the microphone?
My name is Juha Suni, HSM Energiapalvelut. How sensitive is this system for the variation of the steam temperature?
Temperature, not so much. We capture the heat of the outgoing product gas, and there is thermal mass, and so that will balance out variations. Today, the interface specification is 200 degrees C in, because it's manageable, it's easy to handle. It could be a little bit higher, or up to, let's say, 600 degrees C. That would marginally improve the efficiency, but because of the practicalities, we have limited it to 200, and that's easier to handle and have. But variations, the system will handle if there are any. So if there would be a longer term, let's say, a drop in the temperature, the system would then use trim heaters to compensate for that. Essentially, this is a heat-consuming device. We try to operate it at a thermoneutral point so that the resistive losses in the cells produce the amount of heat that the reaction heat sort of removes from there. But this kind of variations can be compensated for by heaters.
Thank you for the question. Thank you for the answer. And I think now it's time for the panel discussion. And while the panelists come on the stage, I can introduce them. So please come here, and then I can see that there are people who came late to this session, so I'll have a short introduction still. So Juha Ripatti still standing there. So he's he's here. So he's the head of business intelligence in West Energy, which can be also seen as a circular economy company. Juha has been responsible for managing the strategic development project of West Energy since 2019. While he has been working for the company, it has had a leading role in the fields of power-to-X and carbon capture, usage and storage technologies with its partners CPC Finland, Prime Capital and Copper Energia. Currently, West Energy has ongoing the first full-scale carbon capture project for waste to energy in Finland. Thank you, Juha, for being here. If I take Eija next, so Eija already has spoken and I have introduced her once, but just a recap of just a few words. So Eija comes from Sodankylä Geophysical Observatory of the University of Oulu, and her main research topic is natural hazards and their effect to the critical infrastructures. And Eija is also exploring how solar disturbances transport energy to the atmosphere and on ground. Thank you, Eija, again. Then we have Tuomas here, and Tuomas already had a speech, but still for those who came late. So Tuomas has worked with high-temperature electrochemical systems for quite some time, and he has had multiple roles ranging from the fundamental systems R&D to supply chain development, and he has several patents around fuel cells and electrolyzer systems. And yeah, I would say that's about Tuomas. And then we still have Shekhar here. And Shekhar is from Danfoss Drives. And he's originally from India and now based here in Vaasa. He's heading Global Electrification Business Unit in Danfoss Drives. And the business unit is operating with the startup mentality in large Danfoss organization. The unit has grown more than 5 times in 5 last years, and Shekhar has 30+ years of hands-on to management experience in motor drives and electrification through power conversion applications. Electrification business unit focuses on offering power converters to applications of strategic focus areas such as electrolyzers for green hydrogen, smart grid and energy storage solutions, heavy-duty fast charging, as well as electrification of ports and vessels offshore. And by the way, these are also the topics of Fossil Free Future program, if you didn't notice. Right, so electrification, the business unit, will be hiring new talents, and it will be working closely with universities and conducting research together with its stakeholder partners in the program ecosystem. Right, and that was the introduction. Now you can sit down. Thank you. Right. Yeah, and there are some free chairs here if somebody dares to come up front. Otherwise, you have to stand.
Nice. Yes, I think the ventilation is really good.
Okay. Moving on. So, this is now the panel. We have 4 questions, and each question you can also see it, and then the panelists can answer the questions in their turn, and then if we have time, there's hopefully some time for the comments or questions from the audience. So that's the way to go forward. Right, so the first question is, in the theme or topic of green hydrogen of today and tomorrow. So, what is the current technology development status and what are the gaps in having the perfect solution for green hydrogen production in place? And if we start with Convion and Tuomas, if you could first say what you think.
Yeah, no matter how tempted I would be to pitch a perfect solution, I think it's worthwhile also to build the less perfect first generation solutions, because it's about continuous learning. And as I mentioned, the hydrogen projects today are mostly based on quite conventional technology, but it's still it's a learning opportunity for building organization, integration, legislative learning. So it has a lot of value. Obviously, being representative of a technology company, we see that there's still plenty of potential to go further, improve the competitiveness by technological solutions, and therefore I believe it's important to sort of keep open eyes for new possibilities and not just optimize around what we have today. It's a work in progress, and we will introduce much better and competitive solutions that will extend the range of green hydrogen.
Okay, thank you, Tuomas. And then if we continue, Shekhar, what's your answer, and do you agree with Tuomas, or do you have something else?
Yeah, we are in Finland, Pia, and you are asking a perfect solution. Do you think we will ever say that we will have a perfect solution? We will always say there is something to be still developed, right?
Agree.
So that's what Tuomas is also saying to you. I have studied physics, and I have studied power electronics and work in Danfoss. So I will stick to that area, not widen the area. There are other colleagues who can talk about space and also electrolysis process and waste energy. But if I say there are technology point of view, there are two high-level power electronics technologies which are used to, when you do green hydrogen, you need to have an electrolysis process, and then to electrolysis you need a DC power. This is converted from AC. So rectifier technology, and there are two high-level rectifier technology, thyristor-based technology, which is very traditional, and the IGBT-based technology, which Danfoss is promoting as well. Why? It's obvious reasons. Whether you take about up to 10 megawatts of hydrogen plant, or you talk about hundreds of megawatts, which is typically industry use, and then you talk a very large scale, more than 250 megawatts to gigawatt. Anywhere you can use this technology with the building blocks. It has its own advantages. You want to make the grid stable, so integrated low harmonics, reactive power compensation. You want to have a low DC ripple, so also take care of that. So all those things are obviously there. Are we developing something new? Yes, we are developing new technology. What is the focus? The focus is on how can we improve the energy efficiency even further by using the new technologies. So that will make the business case even more viable. So I would say you have some word there called gaps. I would say there are no really gaps for us to wait or stop. We can go on, and while we go on, we can keep on improving and do it even more better. That's where we are today.
Thank you, Shekhar. Incremental improvement. Good. What about West Energy and Juha? What are your thoughts?
Well, I have to agree with the gentleman here. I think we have enough technology to really move on and build these systems in a large scale. But I must agree, I mean, it would be nice to have a high megawatt scale, long lifetime SOEC cell stack in the near future, because it would make a lot of these business cases a lot more interesting. But yes, I think overall, and also on the foundation of what you said, I think in a European context, when we are talking about producing green hydrogen RFNBO, with the kind of strict regulations we have in place on how to do it, to have the technology to be able to operate with a grid that is volatile, to optimize the production, use, and storage of the hydrogen, I think it requires a lot of technologies on the side of on the hardware, but also on the software side, so to say, how we operate and run these systems. Because if you try to make your business case and you make a commercial case, you need to understand this really well. And I think even for us, we operate a waste to energy plant, so we are far out of the traditional business of hydrogen production. But let's say having these systems in place to aid in operating the systems right, that's quite important.
Thank you, Juha. And then what about research? You probably have something else to say, Eija.
Oh yes. Oh yes, I do. So I agree with everybody that there is no perfect solution, but maybe we can start thinking here a little bit in the same way as we do in science, that we are searching for truth, And everything that we know at the moment is the perfect solution. So it is a perfect solution for today, so as well as we can do it today. And then we can make a plan for 1 year, so 1 year plan, 5-year plan, 10-year plan, and we can have a wish to have improvements, and we can then work for better solutions for those times. And then we can see whether we reached those or whether we set them too high. And in space sector, building something new, it takes even longer time than in other business sectors. It is very typical to think that quartal is 25 years, so it really needs patience. But whenever something new is done, then it's really new.
Yeah.
So it depends on the sector. How much time do you need for finding this perfect solution?
Thank you, Eija. So that was not a helicopter view, it was a, I don't know, sun view.
Okay, fair enough.
Yeah. Good, thank you. Do we have any time for, okay, so we have time for at least one question from the audience related to this first question, of course. Any thoughts? I know these are tough questions. Okay, if not now, maybe.
There was one. There was one
Okay,
at the back.
good. Thank you.
Sarikola from the Energy Sampo. Energy Sampo is working for the systemic solutions and systemic innovations, and I guess that it's a little bit different thing to have the technology components and have a working system. So how would you reflect the readiness from the system point of view?
Who wants to, I know, again, not a, yeah,
I can
Shekar,
start
please.
and then you can just... this is new, right? I mean, of course, the electrolyzers do exist. But what is new is that we are talking about green hydrogen. The existing install base is all gray. So there is a lot of new parameters to learn and to have it available. That means we need to have a green energy, or we need to define how fast we need to have a green energy. Maybe not from the day one, what kind of contracts. So I understand when Sari is talking about systemic solution, it's all about understanding how to get all these parameters, right from commercial as well as technical parameters, infrastructure, installation parameters. And that is so good. It's new, and I don't think we have already acquired that knowledge, so we need to build it. One of the technique we use when we are doing something first time is we simulate. And we go and measure with whatever real is available to see that how near we have. And I think this is one technique we have been using, have been investing, and it proves a lot. Because then we are able to a little bit predict based on our simulations that when we start talking about the large scale, you have 250 megawatts, 1 gigawatt scale. Of course, it's not existing today, but based on something what is existing and simulation, we are able to much more predict that, okay, what kind of performance we are able to talk.
Yeah,
That's
good.
one example.
Maybe if I can add, you mentioned infrastructure, and I think it's really important in the sense that, of course, we have, at least in Finland, at least for now, a very robust energy infrastructure on the electricity side. What we don't have, I mean, even in Europe, we have, many countries have gas grids, but a hydrogen grid doesn't exist. So you have, on one hand, a lack of freedom, so to say, in creating this system of systems. And of course, that infrastructure is really important if we want to scale up to a much higher level than we are now. Now we are talking about point usage of hydrogen. What we really want to have is a system of interconnections between these different producers and users to have a hydrogen ecosystem.
Yes. Yeah, a quick answer, Tuomas. Yeah.
Very quick answer. There's always, when you build systems with some parts that are not perfect or not ideal, not fully mature, there's a possibility or a danger of so-called lock-in. So you start building best practices and value chains around how you optimize around the weaknesses of a technology. That's something we should be wary of. Of course, I'm pitching for next generation technology, but this is something to be taken into account, that we don't just get used to what we have and get stuck with that, but have something better next year and remain technology agnostic.
Yeah, it was about the incremental
Yes.
improvements. Yeah, good. Unfortunately, a good discussion, but I'm stopping it and jumping to the next question, which is about the knowledge and competence. Again, gaps, I know, awful. So the question is, what knowledge and competence gaps do we have in green hydrogen development, and how can we ensure those gaps are fulfilled? And now if we start with Eija and the research university perspective, please.
Okay, so as in all new infrastructure building projects, it needs to involve risk analysis, and that risk analysis shouldn't be only limited for those most common risks. And all this existing information from national risk analysis, each region in Finland have own regional risk analysis. Those could be used for defining the risk so that it is clear that all of those that are already identified for those areas is considered. So it is very easy to just say that, okay, we need to think that whether it's raining, whether it's lack of this and that, but all kind of probabilities should be considered beforehand. And in risk analysis, there are risks called black swans, which means that something is very rare, but it is possible. In science, we also have, in addition of black swans, we have white rhinos. And it means that there are risks that we don't know. And there we come back to the innovation. So we need to have a capability to see to the future, and it's really challenging. So we need to understand how the society develops so that we can estimate what kind of new risks are coming, and that's challenging. And how we can ensure that those gaps are fulfilled with hard work and a lot of thinking and discussion with different fields.
Yeah, that's good thinking. What about Shekhar? How would you answer to the question?
I will start with what Sari was bringing, that there is how to build systems, right? So clearly there is one gap there. So far we have in Danfoss what we have installed base doing many demos is something like near to 100 megawatts. Small projects, few years back we started starting from few hundred kilowatts to megawatts. Nowadays it's 20 megawatt. So what we have learned from all these running examples, what we know very clearly is that we don't know everything. So we need to learn. There are many new parameters. So I think, and then we touched base about infrastructure, we touched base about, there are more areas like regulations, policies, certification that needs to happen. Not everything is clear. But certainly, even many times we think that in industry we know everything. I'm coming from industry, working there. But it's not necessarily all there. So we need to work together with educational systems, universities, also those who are sitting on the knowledge, working together with them to understand and close these gaps.
Yeah, agree. Collaboration comes there as well. What about Tuomas and Convion? How would you see an answer to this question?
Yeah, when there's a transformation where new technology is very central, we often think of the nerdy deep tech things as the competence areas, but those are the ones that we're probably most aware of. And of course there are some specific areas. For example, if you think of electrification as a big wave and hydrogen is as like a sub-wave of that, and there's going to be a lot of competition between the different areas of the same people, same talent. So that's not, it's not that it's lacking, it's just that there's short supply. But in the hydrogen cluster Finland, we've discussed a lot about this, that when we start thinking, scaling things up, we are going to need a lot more than just the PhDs and the engineers in the lab. We are going to need installers. We are going to need lawyers. We are going to need all kinds of areas of expertise from other areas that are touching this. And these are probably the ones that we are not fully aware today and may end up in a gap situation.
Yeah, yeah. It's interdisciplinary
Yeah.
type of working, collaboration, and that's might be and can be tough. Good. Well, Juha, what do you think?
Well, basically, you stole my answer right now, because I was going to say the biggest gap from our point of view is competent people. And that also means not just competent people for the end users of this technology, but also the people who are actually manufacturing, designing, manufacturing, building these systems. Because what we can see is and I guess this also applies to many other parts of the green transition, is that you have very, very long lead times. The development and actually scaling up of manufacturing takes time, and if you don't have the competent personnel in these companies to provide these technologies, I mean, we can't install it, and then we don't have a business case. So yes, that would also have been my answer.
Yeah.
Well,
Yeah.
one more message I would give, that while working and while collaborating, traditionally maybe we are we can talk about research, we can talk about we need to investigate some things. And working with universities, we might be starting with the labs. But the speed of energy transition is so fast that we need to little bit adjust our minds that maybe these investigation and researches are not happening in the labs, they are already happening in the field directly. So that is the challenge we see, that we cannot spend a lot of time, 3 to 4 years of time in the laboratories, but we need to go directly on the field. And we need to have a readiness also in the universities as well as in the industries to explore, manage those risks and go to the field to demonstrate.
Yeah, the world is changing. Yeah, Eija, please.
I couldn't agree more with that, because that's exactly what observatories will do. We don't go to lab. Yeah. We always go to the forest and we see that, okay, what are the conditions here? What we can measure here? Okay, let's try this. So we go completely other way around. And then we go to lab and see whether it worked or not.
And maybe to add on this point, and what you also mentioned at the beginning, understanding these risks better and better from the practical experience also basically means that everyone is calculating less of those risks into how they price what they produce and offer. And this also means that at the end of the day, this is the way to scale down the costs of green hydrogen. And that is really important, because at the end of the day, if you're not competitive against other alternatives, you won't get to see your systems develop and flourish.
Yeah, that's so true. Do we have, yeah, okay. So, yes, please, there's this lady here, her hand was up first, I think.
There's also another one.
Yeah, I know. Let's see how much time we have.
Well, thank you. I'm Eva Pongras from the University of Oulu. And in addition to these two knowledge and competence gaps, how about the social license to operate? You are talking about massive infrastructures to be built and risks that we know and don't know. And by the way, thank you for the nightmares, Eija, beforehand. So how are we supposed to gain the social license? How are we supposed to gain social acceptance from people if we ourselves even don't know what are the risks and how it's going to impact their lives?
Who dares to say something?
Maybe I can say at least something from this point of view. I think what we can see, because we work as a company, what also on the policy side of things and in close interaction with different stakeholders. And I think there is a strong will. People want decarbonization, the politicians want decarbonization, the investors want decarbonization, and basically everybody wants it. So in that sense, you have already a foundation to build upon. But of course, one thing which is crucially important is not just, we are building very environmentally efficient systems, but the question is also the sustainability of the resource use. And I think there is one thing where technologies like yours, which don't use as much of rare materials, which may have a very challenging sustainability effect, that is also quite crucial, because we need to build a lot. And if we do it in an unsustainable way, we end up back in square one.
Yeah, it's a complex situation.
This is also it's also an opportunity for the society to reskill and upskill and climb up the productivity ladder. So, as we mentioned, it's not just some PhDs in the lab, but it's people around the country that get new jobs and maybe more comfortable, better paying jobs and learn new things. So they can be part of that. So that is at least part of the answer, I would assume.
Yeah, yeah. I think that we have to continue. I know that there was another hand raised up, but sorry, we continue. Good. Then the third question. What about who should take the financial risk in hydrogen development, and what is the role of governments in this development? And I think this is a hot potato. So let's start with Juha. You already mentioned something about finance at some point. So what's your take?
Well, how we see things, and of course this once again is a European perspective, what we think is the kind of state aid competition we have ongoing at the moment. Well, first of all, Finland, we can never win that, and I think it's also in general a fairly unbalanced way of going forward. Also, I don't think it's sensible to think of this as a nationalization transition, so that we socially buy everything. But yes, I think from a financing point of view, because we can see that there are a lot of these risks, and there's a social demand to do this transformation in a quick pace. What the perfect role, so to say, for the state is, first of all, to nudge things forward where you have technologies that are at a high readiness level but not quite commercial, to push them forward so that the investors are comfortable to invest. Because the fact is that private capital is going to be the answer, and I think there's a lot of capital looking for solutions at the moment. So having that balance is important. But I think the main role of governments is to create the kind of regulatory framework which empowers businesses to do business. So that we, of course, respect all the necessary conditions. We talked about the social responsibility as well, but also so that the best technologies can win. Not so that we cherry pick what we seem to like, independent of whether it's viable from a technological and commercial point of view.
Okay, survival of the fittest. Tuomas, how would you see?
Yeah, I fully agree with what you said. For a small company, finance is always a big issue. It's always very central. But I think I agree that government's role is to catalyze a change. It may assist in creating markets, early markets for actual commercial adoption for products. And first and foremost, governments must create transparent, fair, predictable regulatory process. That's what creates the conditions for private investors to then bear the burden of the risk.
Okay. Yep. What about then Eija? How do you see it from research perspective?
Universities' role is always to do forefront research, but then there is always this question that what kind of research can be funded? There is only very limited amount of funding from ministerial level for that innovative research. So it's kind of loop. Universities have a power, they have persons who are capable of doing new innovations, but how they can get the resources. And when we are talking about something which is in a very, very beginning, which this is not in a very beginning, but when we are talking about something that is very beginning, then how we can find somebody who is funding that work. So that maybe needs to be solved somehow. Of course, more money for universities, that's what did I say? Okay. But then what comes to the role of government, then I think so that the government, yes, needs to take care of the regulations so that it's same for everybody. But also sometimes we say that government will build the main road, and then the role of universities or companies is to build then the road what comes to your building. So government don't build everything, but they build the main facilities or basic things what are needed for getting this things done. So I would say that main road is government's role, but then the own last piece of the road is the role of whoever is doing that business.
Yeah. Shekhar, how do you see this?
I have to say I have a little bit different perspective.
Okay.
Good.
And you be ready with the time to tell me to stop now, because I'm a little bit charged. Because we are talking here about social acceptance, and you are deliberately putting the risk as financial risk. I have a daughter, she's 14 years. We are not talking about the financial risk, we are talking about the climate change. We are talking about whether we are living or we are not living. Is the financial risk more than that? That's a question. I will come to your question, so don't worry. I will not avoid it. If we talk about financial risk, I think I would like to say that it starts from me. I need to take the risk. Of course, I don't have so much money to fix the world, but what I means us, each of us. We are working in industry, we are working in government, we are working in the bank and still hesitating and calculating business cases to decide. I think we need to promote. We need to take a stand. We don't need to think about whether it is accepted or not. I think it's very clear to me that it is about climate change. So in decades further, more and more cities are going to get hotter, non-livable. Is that what we want? Today we are enjoying less population, but all of them are coming to migrate here because it is better weather here. So we need to do something about it. I don't think it's a question about financial risk. At the end of the day, yes. So I think those answers are already given, that everybody, government, infrastructure development, engineers to generate technology, banks to make sure that they promote the right options, all of that has to be done. But I think at the end of the day, it's us. We are there representing.
I mean, as a society, we have taken for centuries a loan on the future with fossil energy, and now it's time to pay.
Yeah.
And quite frankly, there are no options to this transition. It has to work.
If we can create plastic, then we can certainly invest money in doing this.
Good. We are challenged, all of us. I think we still have some time for the questions from the audience. Is there somebody who wants to comment or ask something? I guess, Shekhar, your point was so like a killer, so nobody dares to say anything anymore. Maybe it's good for our health that we continue.
There's one hand.
That's one.
Oh, okay, there's one. Excellent.
Jai had a question.
Can you still elaborate, like what are the roles of governments, for doing the development, hydrogen development? Can you little bit elaborate?
I can say, we can start. I think the risk is already taken by the government. We have a clear roadmap in Finland. We are lucky. We have clear target that in 2030, if I understand correct, Finland plans that more than 10% of the green hydrogen what Europe needs is delivered from Finland. We have a clear plan that by 2035 we are carbon neutral, net zero. By 2040 we are zero emissions, and beyond that we are negative emissions, even helping the rest of the world. What more financial risks needs to be taken? Rest is our job to implement it. So I think the government we are here in Nordic regions quite in a good situation, having good renewable energy prices are varying, but also on an average they are on a very good level compared to the rest of the world. So I think we are in good situation to implement it.
Yeah, just a quick comment.
One possible way of seeing it is that it is our everybody's task, and in each level we can do different things. And whenever the risk comes so large that not any company or university or a single person cannot handle it, then it needs to be everybody's, which is government.
Yeah, absolutely.
Yeah, so this has to be taken personally, the whole thing. Got it. Moving on to the fourth and last question. So, How should the green hydrogen production in a big scale with hundreds of megawatts be conducted in a feasible way in Finland? And in a feasible way, it means also already there's a financial and technological aspect in that word. So if we start with Shekarju, how would you answer to the question?
I like the terminology megawatts. Everything high power is good because we have been already doing some megawatts of install base, and now we are looking forward. We already have a pipeline of few hundreds of megawatts of projects which will be delivered this year. So we will be surely learning how to. I mean, of course, we are not alone. We are not turnkey. It's a very small part of the value chain, I would say, while providing the power supply units. But I think all together, we will learn to execute not just up to 20 megawatt scale, but also 100 plus megawatt scale. And sharing that experience is super important. Then coming back to Finland, there are already announced projects. Right? And we little bit touch base in our discussions about social acceptance. We talked about government needs to create policies and clear guidelines about what means green energy, what we are using, so that it can be called green hydrogen, or will it be called clean hydrogen? So there are differences with that, and sometimes I see that we make a big fuss about it, and then the projects can get delayed by defining. Whatever we are doing, if it is towards not using fossil-based but using non-fossil-based is already good. It's much better than using fossil-based, right? So I think we probably don't need to get involved into these discussions and defining. That will happen. That is underway. In Europe or Nordic region, we are in a much better progress compared to the rest. It's more quite well defined how to do it. So I think learning from these demo cases, what we have done, simulating and extrapolating, and then as we are delivering 100 plus megawatt projects, learning from that, sharing, that will be the one way how we can still do it. It is going to happen.
Yeah, thank you, Shekar. Juha, what's your?
Well, I think this is a perfect opportunity for me to promote ourselves a little bit as well. I mean, we have, as you mentioned, the largest. One of the largest carbon capture projects in all of Finland being planned. Hopefully we can take an investment decision at the end of this year. And of course, this is not just a carbon capture project for West Energy. We have partners here, so CPC Finland and Prime Capital, and they are also building one of the largest green hydrogen methanation plants in Kristinestad, 100 kilometers south. So I think in end of 2026, if we are able to progress on schedule, we should have a perfect example of how to do it in a 200 megawatt scale. And then you need to learn or build on this learning you get from these projects to do the next one and the next one and the next one. One thing you mentioned, and I think it's important, is this regulatory aspect. And as I said, I do think that we also need to find a solution for the big elephant in the room that nobody dares to talk about, and that is nuclear. So how to combine all of these different energy sources that are emission-free for hydrogen production at a large scale for the industries that require indirect electrification through hydrogen. We need to find a solution for that as well. But I think the politics are moving forward.
Globally or Europe-wide, it's quite significant. And it seems that big projects are hard, and maybe the hardest part is to get them off the ground. And after that, it's project management and execution. And maybe it's possible that, because these are sometimes incentivized projects, that the instruments somehow create the conditions for getting stuck at this stage. You would think, as an engineer, I would think that let's build a project that can be extended gradually. That would be less risky, and there would be less of losses. But this is not necessarily how the finance of this project works, and I think this is a problem. Another thing that I would like to introduce here is the sort of technological agnosticism. How do you say that? Like remain agnostic to which new technology you want to introduce, because things happen. These are long planning and permitting cycles, and world changes are in between.
Yeah. Last but not least, Eija, what are your deep words and thoughts?
I can see that the word Finland is bolded there, so I will start with that. So what is special for Finland? Fact-based. So Finland is a large country. If we are aiming a solution for entire country, and I believe we are, so Finland is a huge country. The area is large. It has permanent settlement above Arctic Circle, which is very rare globally. So which means different conditions. Then we have cold winters, which means that we cannot survive. We don't survive if we are lack of heating for 3 months or even 1 month or 1 week. It's painful. So it needs to be fully proofed, whatever we build. And then what is special in Arctic region is the connection to the space, which we need to take into account more than in other areas.
Thank you, Eija. And I think now we have some time for questions, comments from the audience. Can I see a show of hands? Who wants to?
There is one. Sari has a question.
Me again. so I guess one of the challenges, the way I see it, is that, or actually formulated by a person far wiser than I am, so a startup investor and banker, framed the challenge so that these hydrogen systems are startups with the need of industry scale funding. And the question is to Juha, because you seem to be furthest along, and obviously it's a combination of private and public funding. So any best practices to share? How have you tackled this?
Let's say we've hit our head against the wall for a few years, and then we found the right solution. Now, I think it's really about finding a business case that works. Once you do it, everything else, at least so far, has been relatively straightforward. Once the business case, once you can show that, okay, this is going to be viable, then it's an easy time convincing. So how to build that business case, of course, it's always going to depend on the specific conditions. But if you have a market, as we found out, that, okay, there is actually demand for all of our carbon dioxide, so why not develop a project towards that? And it takes its time, of course, but that is maybe my only easy advice I can give. Find a good business case.
Isn't it many times finding more than just one use case and then become the business case much more stronger?
That is true as well. And I think in our case, when we talk about utilizing CO2, we have the fuel side, and fuels for decarbonization are going to be needed, but we are of course also looking beyond that to even more permanent carbon storing products. And that is something that is going to need research, technological development, and a market. And when that market becomes, and that's also a political question then, on how we replace virgin fossil materials, make hydrocarbons for other products than just the transport sector, so to say.
Yeah.
That's where a lot of things still need to happen to make the business case possible.
Good. More questions?
The question there earlier. What about? Yes?
Well, she stole my question, but I can... Yes, Pirita Huotari from Shefla, and as said, she stole my last question about social acceptance, but maybe I can give a part of an answer to this one. So, why Shefla, a huge global company in Finland doing stuff with hydrogen? We have experience of accelerated business technology and business development in a completely other business area from Shefla. And there they experience that in Finland we are able to, through our networks and through this trust culture, able to build technologies, value chains and new businesses faster than what they are used to anywhere else in the world. Yeah. And that is why Shefla is now looking for these networks in Finland. Well, maybe Convion, you have done this already, and you are working in the Hydrogen Council and so on. But I think this is one part of the question why it's possible to do this in Finland.
Thanks.
Thank you. Yeah, that's a good comment. Trust is a glue, how I see it. Glue in collaboration. Without that, we can't collaborate. More questions or comments?
I can give comment that there were a lot. Oh, Laura has.
So Laura Frisk from Danfoss Drives. What we see when we do these hydrogen collaboration projects, for example, is that you already mentioned data. We get lots of data from demonstrators and so on, but quite often it's confidential, so we cannot share. So how do you see, how should we deal with that? Any ideas how to improve? Because I see that kind of restricts how we do collaboration, how we can proceed.
Yeah, good tricky question, Laura. Data belongs to someone, right? And everyone has certain position in the value chain, so, and everyone is learning. So sometimes there is a little bit of, let's say, conservativeness to release the data because we are not so sure. We are in learning phase. Sometimes it is related to patents and IPRs and so on. But the output or generic output of the data, like we are doing that, whatever we are learning from the simulation models, we are quite open to share with whoever, not in the Tori in the market, but whoever is related in the value chain, we are of course collaborating. And that's also another reason our business model is like that we are always partnering. But I think you have a good point that we have to do this fast. And there is a lot of space. There is actually, I say that there is no competition because there is so much space to do this that everybody can do it. So how do we share the data? I don't have a perfect answer for you.
Maybe to build up on this, I don't have a perfect answer either, and I think the question of IPR is really challenging in this sense. But of course, the trust-building exercise of building networks, having companies working together. I think Vaasa is a good example because this is like it's a big village. Most people in the business know most people in the business, which means that you have a lower threshold of being able to talk. And then we have organizations like Energy Sampo, which really show how you can actually build that common trust into new projects. So I think this kind of model is needed, but how it turns data into common use, it's still a hard question.
Yeah, please, Eija, you had also something.
Yes, in academic environment, it is very important value to have free data. But what was a little bit misunderstood when the open data regulation were done in Finland was that everybody told that open data means free data. It doesn't mean. There always needs to be resources to make the data free. So it doesn't mean that you need to work 24/7 to give the data whatever is requested from you, but there needs to be resources to do it. And now what has happened during recent years, this new security environment have forced us to rethink about the openness.
Absolutely.
Yes, that's a good comment and good last words. I think the time is up, and I would say thank you all, and thank you for the panelists.
Thank you.
And I would also like to thank the ladies who have put this all together. And there's Johanna, Maria, and Netra. Could you also stand up? Let's give a big applause. Thank you. And as said, so we are looking for partnerships in research and business context. So please contact us if you have any ideas, comments, and thank you, and have a nice rest of the day.